Yeah, I'll just mention, since Jim was talking about Novik, that one thing we concentrated on sugar enhancer types because we wanted to do direct seeding. We've heard from farmers in all the regions that they would like us to be looking at super sweets under transplant conditions. So we're going to start that this year, which again is a response to the farmers. So we're going to be starting on that. We'd like to leave some time for questions, so I'm going to kind of rush through this a bit. This is my current program of breeding for pest resistance. I'm going to talk a little bit about that. We do a lot of effort on breeding for quality sweet corn. And along those lines, I am thinking about starting a actual breeding under organic systems with super sweets transplanted, because that's what the growers in our region are interested in. Breeding for organic systems is a substantial effort. Jared Zeistro, who all of you know, is working on a project with us. Tessa Peters and Ginny Moore, who's kind of hiding in the back. So we have 3 grad students working on organic systems. We have cultivars being sold, organically developed under organic conditions. Who Gets Kissed you've heard about, but there are 4 F1 hybrids that High Mowing is selling that were really truly collaborative. We developed the inbreds, and Jody Lou Smith, the breeder at High Mowing, actually made the hybrids, and she picked out the hybrid she liked the best. So those are out there as well. Currently 9 grad students, as I said, 3 working on organic programs. We have 2 organic nurseries, a big program. I want to really let me just go back to Jared. Jared has a poster here. He's doing a very complex mating design. It's called genomic selection, and genomic selection is all the rage with the field crops now. And what we want to know is if it can be actually applied for a crop where eating quality, flavor is really important. And so that's a big part of what Jared is doing. So you can check out his poster. New varieties or developments this year. We came up with this purple colored one, or segregating for purple color. The key thing is it's delicious. I mean, there's some other purple ones out there that exist, but they're not much to eat. But this one was amazingly good. This is a processing type variety that we're really excited about. And then this is the inbred. This is a hybrid. This is the inbred that makes this hybrid, and very disease resistant. And this inbred is 50%. The inbred is 25% Mexican tropical germplasm, which gives a lot of disease resistance. We are breeding for insect resistance. Believe it or not, there is native insect resistance, non-GM insect resistance. Corn earworm is our biggest problem in the Midwest. European corn borer, quite honestly, is actually being suppressed by all of the BT corn being grown by the field corn growers, but it's still out there to rear its ugly head when it overcomes that resistance. And then another really nasty one is western bean cutworm. So we're trying to look at approaches to breed for resistance there. This is what Ginny Moore is working on. So natural genetic resistance to insects in sweet corn. There's morphological traits, and here you can see some ears, and the morphological trait in this case we're looking at is the length of the husk extending beyond the ear. So here's the tip of the ear, and here's maybe 2 inches of husk. This is helpful in resistance to corn earworm. Here you can see one from the same population that's maybe only got a 1/2 inch. So we're selecting for longer husk length. One of the key things when you select for longer husk length, there's 2 ways to get it. One is to actually get longer husks, and the other one is to get shorter ears. So we're trying to make sure the ears stay at an acceptable length as well. There are natural chemical sources of resistance that corn has, and people throughout, especially the tropical countries, have been using for years. It's not harmful to people, but it does help with insect resistance. There are 2 chemicals, Dimboa, that we know of, that actually controls leaf feeding in the juvenile plants, and then Mason, which is found in the silks, and again, these are natural chemicals found in the silks, suppresses insect feeding of the silks. So these are things we're looking at. Ginny is selecting for both long husks and combining Mason in individual inbreds. So This just shows you that here's Mason increasing in the silks. And again, this is not in any way harmful to people. Mason increasing in the silks. And then here you see the inhibition of growth of the insect. So Mason is very effective. This is basically 100% inhibition of the larva. So Mason is very effective. I want to tell you that I was talking to one of my grad students about this, or discussing this, and he said, I said, Mason, and Ginny's working with Mason. He said, what is that? And I said, oh, this is a naturally occurring chemical that, that suppresses worm growth. And I said, and there's been a ton of work done on this over the last 30, 40 years, but it all stopped in 1996 when BT was developed. Just stopped all the effort. And he said, well, that was pretty dumb. Yep, that was pretty dumb. The interesting thing about what we're doing here was this will actually benefit conventional growers as well as organic growers. But it's targeted for the organic market. Another insect that's an enormous pest is the corn rootworm. It's an enormous pest in the Midwest. It's actually probably more serious than the earworms, and it prunes off the roots and causes severe lodging. I was actually asked by Aaron Silva to give a talk at the Agronomy Society meeting about breeding for insect resistance. And I threw this in just to remind everyone that here's a pest that's really tough, and I didn't know what we could do about it. Then I remembered, as I was preparing this talk, that I had had this clone in my greenhouse for 40 years. My master's degree mentor, Walton Gallinack, created this clone about 60 years ago. This is a corn Tripsicum hybrid. Tripsicum, for those of you from the southern plains, would know this is, I think it's eastern gamma grass. It's a perennial, and it is completely resistant to the rootworm. So I'm going to dust off this old clone and get it out there. I'm not talking about developing clonally propagated corn, at least not in Wisconsin. This has no frost tolerance, but we are going to start looking to see whether we can extract rootworm resistance from that. And so we'll be starting a project on that. Another area we're working on is competition with weeds. We are looking at altered growth habits, wider leaves, maybe more horizontal leaves, also faster growth. I think that's my next. Wider leaves for more shade, faster growth, better germination, coming out of the ground quicker. That's one of the reasons people like transplanting so much is you're putting a bigger plant out there. Getting those plants to grow faster, germinate better. Taller plants, we know from our studies, compete better with weeds. We have to be careful about how tall, but taller is another thing we can do. This all is the work, well, it's not all the work. This is Tessa Peters. She's currently working on this now. This is actually work that Jared Zeistro did when he was doing a master's with me. And what we're doing here is using a model weed. Here's a row of corn, and then here we planted a row of sorghum, forage sorghum. So this is our weed here, and so we're seeing what kind of competition we get. And down here is what that field looked like at getting close to harvest time. So you can see the density that we had here. So we're looking at higher density tolerance. Tessa is actually growing corn, sweet corn, inbreds or developing inbreds growing at a 50% higher density, meaning more plants per acre. And this is the technique that field corn breeders have used to develop improved weed competition. This is also a technique that the seed companies love because they're going to sell 50% more seed. But that's not our purpose. Our purpose is to get higher density tolerance, and Tessa's working on that. And then we're also working on the development of synthetic populations. I was looking at Jared's slides. Jared's sitting in the back there for his for this presentation, and one of his slides said a terrible name. Synthetic is a terrible name. This is not synthetic biology. This is an old-fashioned way of developing plant varieties. Synthetic populations are, well, let me tell you the reason we are looking at these, is it's hard from what my conversations with people who are interested in organically produced sweet corn seed, it's hard to produce these, the hybrids, because you have to grow inbreds under organic conditions, and inbreds are notoriously unable to compete with weeds. So this becomes a problem for the organic seed grower. Well, one possible solution is the idea of using a synthetic. And a synthetic, do I have something else on my slide here? Let me see. No? This is something I stole off the web this morning to show you what a synthetic is. You create a population, a variation. This is actually a turf grass synthetic, but the idea is the same. You grow these individuals out in your field, out in an organic field. You look for ones that have desirable characteristics, flavor, tenderness, what have you. You grow them out in the field. You select the best ones. Now, in our case, because we're dealing with seed-propagated crops, we would self-pollinate. This is clonal, but you would self-pollinate all of these plants and select the best ones. You would save the best ones, and you do this repeatedly. And then when you had a group of these plants, you would create your synthetic. What you would do is you would intermate these plants, and then generally you make a syn2 where you again intermate. So, and this is the seed that would be sold to the farmer. And so the increase, the big increase of seed that we would do under organic conditions, we could do this under organic as well, but the big increase of seed, you would be actually, the seed producer would actually be growing very vigorous synthetic plants. So really competitive with weeds. And I was down in South America in January, and I saw some of Tessa's synthetics, and they were this tall and really leafy and very competitive. So this is a way, whether it's useful or not, we'll see, whether it's adopted by the farmers. But the other thing about the synthetic is that you can breed from it. The farmer can take this synthetic onto their farm, and they can select and develop new line or new open pollinated varieties. So it has that desirability. But then the other trick with the synthetic is if you keep these inbreds in your cold storage, and let's say a farmer has a failure with their synthetic that they've been developing, or maybe horribly it gets contaminated with GM and they can't use it anymore, we can go back and make the original synthetic again. So we can then sell the farmer the seed that they lost or whatever happened to that seed. So it actually has a lot of desirable characteristics. And I'm getting the hook. So, oh, last thing, culinary corns. A lot of people say our super sweets are too sweet, and the chefs agree. So we're looking at other types of corn that could be used for savory dishes. And we're working with Lane on this and Julie Dawson, and this is a really exciting area. But I'll just leave that picture.